Time series basics for banking. In this lesson we will learn how to use time series analysis for common banking problems. Time series data is everywhere in banking, from transactions to risk monitoring. Understanding time series helps banks detect fraud, forecast cash flows, and manage accounts. By the end, you will know how to inspect, plot, and analyze banking transaction streams in Python. We will build skills from beginner to advanced and solve a real banking scenario step by step. Running the cell now. We import pandas to work with tabular data. We import NumPy to create random and numerical data. We import matplotlib for plotting graphs. We import Seaborn for more attractive statistical plots. We import warnings to optionally ignore warnings. We suppress warnings so the outputs stay readable. We set the random seed to 42 for reproducibility. Running the cell now. What is time series data in banking? Time series data means observations indexed in time order. Banking transaction logs are time series. Each entry has a time, amount, and metadata. Typical columns: transaction ID, date or time, customer ID, amount, type, channel. A common beginner mistake is forgetting to sort by time or not parsing dates as datetime. Getting time handling wrong can ruin forecasting or anomaly detection. We need to be careful to use the right frequency, handle missing times, and ensure correctness. Running the cell now. We are going to create a synthetic transactions dataset for banking. We set the total number of transactions to 1,000. We set the number of customers to 200. We start to build a data frame with multiple columns. We assign unique transaction IDs from 1 up to the number of transactions. We randomly allocate customer IDs to each transaction. We generate random amounts with a realistic distribution for banking transactions. We randomly pick transaction types, either debit or credit. We randomly assign the channel, such as ATM or online. We generate transaction timestamps at hourly frequency, starting from the 1st of January 2024. We put it all together into the data frame. We print out the top 3 transactions to see what we have created. Running the cell now. This output shows the first 3 rows of a synthetic banking transactions data frame, where each row is a transaction with columns like transaction ID, customer ID, amount, type, channel, and a properly formatted date time. Notice that a date column is sorted sequentially by hour, which reflects correct time indexing, crucial for time series analysis. This example highlights the importance of having well-structured and time-ordered data as a foundation before performing any time-dependent banking analytics. Practice: try changing the frequency from hourly to daily and see how your dataset changes. Now, let us check that our date column is a date time and our table is sorted by date. We print out the data types for all columns. We check if the dates are sorted in increasing order from oldest to newest. Running the cell now. This output confirms that the date column is correctly parsed as a date time type and that the transactions are sorted in ascending time order. Notice the key columns like transaction ID, customer ID, and the amount have appropriate data types, which is crucial for accurate time series analysis. Ensuring proper date parsing and ordering prevents common mistakes that can distort forecasting or anomaly detection in banking data. Challenge: what happens to your analysis if dates are out of order? Let us look for time trends by visualizing the number of transactions each day. We make sure the date column is in datetime format. We set the date column as our data frame index. We resample transactions by day and count them. We make the plot wider for easier viewing. We use Seaborn to plot daily transaction counts with dots. We add a title to the plot. We label the x-axis as date. We label the y-axis as transaction count. We enable grid lines for clarity. We display the resulting line plot. Running the cell now. This plot shows the daily count of transactions over time, highlighting how the number of transactions fluctuates each day. Notice the importance of converting the date column to datetime and setting it as the index, which enables proper resampling by day. This step ensures accurate time series analysis and prevents errors in trends or forecasting. Adjust the resample frequency to weekly, W, or monthly, M, and replot. Subscribe to our channel for more tutorials like this. A common banking analysis is to see how much money flows in or out per day. We sum transaction amounts per day using resample. We print the total transaction volumes for the first few days. Running the cell now. Here we see the total transaction amounts aggregated by day, which confirms that the data is properly indexed by date and sorted in time order. Notice the daily sums reflect combined transaction values, a key step for analyzing trends or patterns over time. This aggregation is essential before forecasting or anomaly detection, highlighting why correct datetime parsing and sorting matter. Explore: is volume stable day to day, or are there spikes? Let us visualize the daily total transaction amount. We create a wide plot for readability. We use Seaborn to make the line plot. We give the plot a clear title. We label the time axis. We label the amount axis. We show the grid for easier reading. We display the plot. Running the cell now. This line plot shows the total transaction amount aggregated for each day, highlighting trends and patterns over time. Notice the continuous timeline on the x-axis, which confirms the data is properly sorted and aggregated by date, a crucial step in time series analysis. This visualization helps demonstrate how handling dates correctly enables meaningful insights in banking transaction data. Think: how could a bank use this plot to spot unusual activity or plan for busy days? Let us smooth out short-term fluctuations by looking at a 7-day moving average. We calculate a 7-day rolling mean on the daily amounts. We make a wide plot for both lines. We plot the daily totals. We plot the rolling 7-day average. We add a title for context. We label the time axis. We label the amount axis. We add a legend so both lines are clear. We enable grid lines. We show the result. Running the cell now. This plot compares daily transaction amounts with their 7-day rolling average, smoothing out short-term fluctuations to highlight trends over time. Notice how the rolling average creates a smoother line that helps reveal underlying patterns in the time series data, which is crucial for accurate forecasting and anomaly detection in banking transactions. This illustrates the importance of correctly handling time-indexed data to extract meaningful insights. Practice: change the window size to 14 or 30 and compare the smoothing effect. Now, let us look for monthly patterns by counting transactions by month. We resample transaction IDs by month and count them. We make a bar plot that is easy to read. We display month names on the x-axis and the count on the y-axis. We add a title for clarity. We label the x-axis as month. We label the y-axis as transaction count. We tilt the x-axis labels for readability. We show the bar chart. Running the cell now. This bar plot shows the monthly transaction counts, revealing clear seasonality in banking activity over time. Notice the trend and peaks in certain months, which highlights why sorting and properly indexing by time is crucial for accurate time series analysis. This step ensures we capture meaningful patterns essential for forecasting and detecting anomalies in transaction data. Reflect: do you see months with more or fewer transactions? What could explain this pattern? Banks need to detect days when something unusual happens. We calculate the average daily amount. We get the standard deviation of daily amounts. We select days where transaction volumes are much higher or lower than normal. We print out the dates and amounts for these anomalous days. We print the result. Running the cell now. This output lists the dates where daily transaction volumes significantly deviate from the average, identified using a threshold of 2 standard deviations. Notice how these anomaly days stand out with unusually high or low total amounts, which is crucial for spotting irregular activity in time series banking data. This step shows the importance of correctly aggregated and sorted time index data for effective anomaly detection. Discuss, why might a very low or very high day signal fraud, system problems, or holiday effects? Banks often see patterns by the day of the week. We create a new column showing which day of the week each transaction happened. We group by day name and calculate the average amount for each day, sorting in week order. We make a bar plot of these means. We add a plot title. We label the days on the x-axis. We label the y-axis for average amount. We show the chart. Running the cell now. Here, we've added a weekday column to our time index transactions to explore how average amounts vary by day of the week. Notice the bar chart ranks weekdays in their natural order, revealing patterns like higher spending on certain days, which underscores the importance of correctly handling and ordering time-based data. This step demonstrates how enriching time series data with derived time features helps uncover business insights in banking. Explore, what business changes or events could cause weekly cycles in customer banking. Sometimes banking data has missing days, maybe due to outages or public holidays. We create a full range of dates from the start to the end of our data, daily. We re-index our daily totals to this full list. We find any days where we have missing data by looking for missing values. We print the dates of missing days as a list. Running the cell now. This output shows that there are no missing days in the time series after re-indexing, meaning the transaction data covers every day continuously within the date range. Notice how the code fills in any potential gaps by creating a complete daily date range and checks for nans to ensure no days are missing. This step is crucial for maintaining data quality, as missing dates can lead to inaccurate forecasting or anomaly detection in banking time series. Tip: always check for missing times before developing a forecasting model. If dates are not correctly stored as datetime, operations will fail. We reset the index to restore the date column as a column. We force the date column to string type. We try to convert the string dates back to datetime. If it works, we confirm success. If there is an error, we catch it and print what went wrong. Running the cell now. Here we see that the date column, originally converted to string, was successfully parsed back to datetime without errors. This step is crucial because proper datetime formatting ensures time series data can be correctly sorted and analyzed in banking transactions. The successful conversion confirms the code's intent to prevent common mistakes that would disrupt time-dependent analyses like forecasting or anomaly detection. Remember, always check your data types before resampling or time analysis. If we have missing days, we may want to fill these gaps before analysis. We use simple interpolation to estimate missing daily totals. We make a wide plot for clarity. We plot the interpolated daily transaction totals. We add a title. We show the grid for reference. We show a legend for clarity. We display the results. Running the cell now. This line plot shows the daily transaction totals after filling missing values using interpolation, which smoothly estimates gaps based on surrounding data points. Notice the consistent trend without abrupt drops, ensuring the time series remains continuous and meaningful for analysis. This step is crucial to avoid errors in time-dependent models by properly handling missing timestamps in banking transaction logs. Reflect: is interpolation always safe in banking? When should you avoid filling missing values? It is best practice to never edit your raw data directly. We make a deep copy of the data frame as a backup. We check if the data and its copy are identical. Running the cell now. This output confirms that the copied data frame df_or is an exact duplicate of the original df, ensuring the raw data remains unchanged. This practice is crucial in time series banking data to preserve the original transaction logs, allowing safe experimentation like sorting or datetime parsing without risking data loss or corruption. Always working on a copy maintains data integrity for accurate forecasting and analysis. Tip: if you make a mistake, you can always restart from the original input. Instead of manual loops, use Pandas resample for efficient aggregation. We filter our data for debit transactions, then sum amounts by day. We do the same for credit transactions. We make a large plot for both time series. We plot debit totals. We plot credit totals. We add a descriptive title. We label the date axis. We label the amount axis. We add a legend for clarity. We enable grid lines. We show the results. Running the cell now. This plot shows the daily totals of debit and credit transactions over time, with amounts aggregated using resample, a key step for accurate time series analysis. Notice the smooth trends and clear time index, demonstrating that dates were correctly parsed and sorted. This approach avoids common pitfalls like loops and unsorted data, enabling reliable financial forecasting and anomaly detection. Reminder: resample and Group B are fast and reliable for time-based analysis in banking. Now, we will solve a real-world problem. Suppose the bank wants to spot days a specific customer suddenly spends much more than usual. We pick a customer with the most transactions to focus on. We extract data for this customer only. We filter for debit transactions, representing cash outflow. We resample to get daily totals for this customer. We use a window of 7 days for a rolling mean. We look for days where spending is much greater than the recent average. We print any detected outflow anomalies for this customer. If there are none, we say so. Running the cell now. This output shows that for the most active customer, no daily cash outflow exceeded the typical range defined by a 7-day rolling mean plus 2 standard deviations. Notice how the code relies on properly resampled and time-indexed transaction amounts to accurately detect anomalies. This reinforces the lesson point: correctly handling time series data and sorting by date is crucial for meaningful anomaly detection in banking transactions. Can you adapt this logic to spot cash outflow anomalies for every customer? Let us visualize the daily debit totals and mark any anomaly days. We set up the plot size. We plot the total daily cash outflow for this customer. We show the rolling weekly average as a dashed line. We mark anomaly days in red. We add a useful plot title. We label the x-axis. We label the y-axis. We show a legend for all plotted lines and markers. We enable the grid. We optimize layout for display. We save the figure as an image file. We print confirmation that the image has been saved. Running the cell now. This output confirms that the time series plot of a customer's daily cash outflow, including the raw data, 7-day rolling average, and detected anomalies, was successfully saved. Notice how the rolling mean smooths short-term fluctuations for clearer trend identification, while red dots highlight unusual outflow spikes, key steps for reliable anomaly detection in banking data. This reinforces the importance of proper time indexing and visualization in understanding temporal transaction patterns. Now opening the image so we can visually inspect the detected anomaly. Open the image to see the cash outflow pattern and identify the anomaly visually. Great work! Where to next? You have learned the foundations of time series analysis for banking data. You can now inspect time-based trends, spot anomalies, and visualize transaction patterns. For practice, try using these tools on your own bank statement, but be safe with your data. Check out our full course and subscribe to our channel for more real banking data examples. Next, explore forecasting techniques, anomaly detection, and customer segmentation. Running the cell now.